Okay, so superalloys. I'm going to make sort of a bold claim and say this is probably the metal or the material system that's done more to bring people closer together and to shrink the world out of anything that's been developed so far, right? I mean, steel led to the industrial age. Nickel and silicon led to the communication age, I would say, right? You know, if you think about how ubiquitous air travel is, right? How many people flew over Thanksgiving? Right? Maybe not so much here because everyone's from Ohio, but right? Is there anyone here that has never been on an aircraft? Right? So, you know, I don't like to think of myself as that old, but I still had plenty of friends who, in high school, living in a major metropolitan area, had never been on an airplane, right? And I'm only in my early 40s. If you think about what air travel was in the 60s and 70s, it was a big deal. People put on their best clothes to get on an airplane, right? Now it's a commodity, right? And people don't think about anything of buying an airplane ticket and flying. And it's all completely because of nickel superalloys and the GammaPrime system, right? So if we look at a modern aircraft engine, we pointed out a lot of titanium last week, mostly up in the fan, right, and the low pressure compressor. But basically the whole, and some heat and some shielding back here, but basically the whole back end of this engine, everything that sees temperature is nickel. And these are the most sophisticated, highly engineered alloys that are out there. And just sort of showing where we are, right? I mean, you probably in freshman and sophomore year had an overview of a turbine engine in one of your engineering design classes, but it works just like any other engine, right? It's suck, squeeze, blow, right? That's the basic operating principle of any heat engine. But right, you have compressor, inject fuel, light it on fire, you get expansion across the turbine that lets you do work. But if we look at the particularly the operating temperature, right, at the T41 stage here, right, we're at modern engines now are approaching 1625 for military engines, a little lower than that for civilian engines, right? So the interesting thing is this pressure ratio, right? Why between engines of about the time you guys were born between now, why are we seeing a drop in pressures? It's that high bypass turbofan, right? Not nearly as much air is going through the engine, right? Most of it is, right? In the older engines, basically everything went through the jet. Now the big fans on the front are like big propellers, and we're spinning them by much more efficient and much higher operating temperatures. Why is the right? That's given by the bypass ratio here, right? Right. So this is how much air goes through the engine divided by how much goes around the outside, right? So now it's about equal parts. But why is there such a big impetus for higher and higher operating temperatures? What does that get you? What? Heat cycle efficiency, right? It's basic, first year engineering thermodynamics, steam table thermodynamics, right? The greater the difference between your hot and your cold reservoir, the more efficient your engine is, right? Basically, a 100-degree temperature increase translates to right now about $1 billion a year across the entire fleet of savings in fuel. Right? It's significant. Right? And this is all materials, right? It's all about, can we survive? Can we put in materials that survive? Right now, we're running engines that are above the melting point of some of the alloys that are making up the blades, all because of combination of very high strengths, active cooling, and thermal barrier coatings. Right. Obviously, the metal itself doesn't see that temperature. It's in an environment that is above its melting temperature. Right. And so here we see the complexity of a modern disc on modern blade. On Friday, I'll bring one in that's got the yttrium stabilizer zirconia thermal barrier coating on it. But you can see, right, there's cooling channels, right? This is a hollow blade, right? So this is an incredibly intricate casting, and it's cast as a single crystal, right? I don't know if did most of you know that modern turbine blades are actually single crystals. Right? Why single crystals? Better creep properties. Right? So our major design constraints are going to be creep and fatigue, specifically low cycle fatigue. Right? Okay, so when I say superalloy, what do I mean then? Right, so very simply, metallic alloy, which can be used at exceptionally high temperatures, homologous temperatures of 0.7 and above, right? So the use temperatures are going to be 70% of melting temperature. Why is that significant? What typically happens to properties around that? They take a nosedive, right? Okay, so we need creep, high temperatures, oxidation resistance. We don't want any high temperature corrosion, right? And there are superalloy systems based on iron, cobalt, and nickel. We're going to focus on nickel because that's what's basically used. Cobalt, why is a lot of research going on to cobalt superalloys right now?
Higher temp capabilities, but it's
higher.
It's not capable of strength.
Yeah, so it's higher melting temperature, right? So if we could push, the problem is we don't have with cobalt, we currently don't have the strength, and we'll talk about that as we go through. So right now, nickel still reigns supreme. So let's take a quick look at our nickel aluminum phase diagram. So the alloy system that we're really interested in is nickel aluminum titanium. But looking at ternaries is a little complicated. So let's just start with nickel aluminum right now. And so if we see at about 80% or so nickel, right? We're in the two-phase gamma prime region. and we go up to quite high temperatures before we dissolve our gamma prime, right? We go full nickel in, we go full gamma above our solvus into a solid state regime before we start to see any melting, right? And this is basically our main processing window, right? We're going to process, come up, super solvus, dissolve all of our gamma prime out, come down, and precipitate a gamma prime structure, and the two-phase microstructure is going to be our main strengthener, right? Now, if we look at the other side, if we look at the aluminum nickel side, right, there's no appreciable solubility of nickel in aluminum, right? It's basically line compounds, pure nickel or pure aluminum and the intermetallic. Whereas on the other side we have roughly 25% solubility of aluminum in nickel. Ah, dang it, there's a typo. So scratch out less than and put greater. Greater than. It's funny, you know, how many times I look at these things and don't pick them up, but then when I'm presenting them, I find all the typos. So this is basically what we said, the two-phase gamma prime microstructure. The gamma prime is going to be responsible for the incredible resistance to creep, right? And so if we look at the ternary now, this is at 973 Kelvin, right? This is the two-phase region that we're mostly going to be interested in. Gamma out here, gamma prime, right? And you can see that most of the titanium and aluminum are going to tend to segregate to the gamma prime. So here's the gamma prime structure, right? The important thing to notice about this is L12 crystal structure. It's an ordered compound, right? It's a true ordered structure, right? We saw a little bit of titanium with an ordered structure, but when we talked about steel and aluminum, we talked a lot about particle strengthening, but they were not. We either talked about intermetallics like cementite, right? But we didn't really talk about ordered compounds. Okay, so before I go there, right, I say it's a primitive cubic unit cell, right? To me, it looks like FCC, right? So if this is primitive cubic, what's the motif? Right? How does this translate to primitive cubic? Right? What's the repeating unit? Right? So if it's primitive cubic, any ideas? Crystallography reminder? This aluminum, right, and 3 nickel atoms, right? That's our motif. Our lattice sites are the corners of the cube. So if we repeat this cluster of 4 atoms, translate it, we end up with this, with the L12 structure, right? Why is this structure responsible for for strengthening, right? Well, we're going to basically spend all of Wednesday talking about this, but right, as a bit of an introduction, where's the huge strengthening capability come from this? What's that? Yeah, right. What happens as a dislocation comes through here, right? Right. If we have a 1/2 110 dislocation, what's it going to do? It's going to translate aluminum onto nickel and nickel onto aluminum site, right? So we need 2 dislocations to come through to put us back to our regular configuration. So a regular FCC dislocation, 1/2, 110, becomes a superpartial in the GammaPrime and causes a APB, right? Now, if the partials are, if the FCC 1/2, 110 are separated into 2 Shockley partials, when they come through, they form much more complex fault structures, right? So we basically have, we're going to have dislocations that want to stay together, pairs of dislocations that want to stay together, and chemical interactions with the dislocation, not only the typical chiral stress, right? Okay, both phases have the cubic lattice with very similar lattice parameters, right? The gamma prime precipitates in a cube-cube orientation relationship with gamma. So what does that mean? Right? What do I mean by cube-cube? Right? 100 parallel with 100 faces the 100 direction parallel with the 100 direction, right? So there's a perfect basic lattice correspondence. Right? The lattice parameters are very similar, so the gamma prime is coherent when with gamma when the precipitant size is very small. And as I said before, dislocations in the gamma are difficult to cut into the gamma prime because the ordering interferes with the dislocation structure, right? Low interfacial energy, right? This coherent or semi-coherent interface is really important for maintaining stability at elevated temperatures, right? The more low energy the interface, the less mobility it has, right? And so we maintain a stable, more stable structure. Okay. So I sort of answered my question already, right? What are the implications of the low interfacial energy, right? Mismatch between gamma and gamma prime can be tailored by alloying. So what's the implications there? Right, we can play with the mismatch. Right? We can play with the properties quite a bit. Right? We can play with the strain field around the dislocation, around the particles. Right? We can play with the shape of the particles by playing with the mismatch. Right? Okay. But as we go through this, we have to remember gamma prime is a real ordered structure, right? So, main contribution to the creep strength, right? It is still relatively ductile, and we'll point this out at the end and talk about it a lot on Wednesday. Strength increases with temperature up to about 700 C. Why do I have that a surprise indicated there? What typically happens with strength and temperature? It decreases, right? So what is it about this gamma prime structure that gives us an increasing strength? I really wish we actually accepted the interrobang as a proper punctuation mark, right? Okay. So looking at the phase stability with temperature, personally, I hate ternary phase diagrams. They always confuse me, right? But we can see here, basically, if we look as we go up in temperature, the gamma phase field expands, right? And if you do your lever rule calculation, so that means at the same concentration of alloying, right? As we go up in temperature, the fraction of gamma prime is going to decrease, right? Right. That makes sense with what we said before, right? We have a solvus, right? So basically, in the ternary, we can go super solvus, dissolve the gamma prime, right? And then precipitate out a uniform and fine dispersion. So schematically, what does the microstructure look like? Well, these are the gamma grains, right? Outlined here. In between the gamma grains, we have what we call primary gamma prime, right? And this is primary. This was gamma prime that was not dissolved during the solution heat treatment, right? Then within the gamma grains, we have particles that are around a little smaller than a micron, 70 to 120 nanometers, sometimes larger. Right, the secondary gamma prime, and then in between we have tertiary gamma prime, which is on the order of nanometers to tens of nanometers. Right, so we have a highly complicated, highly tortuous microstructure. We'll look at real micrographs in just a couple minutes. But if we come back to the nickel, this is reversed. This is the phase diagram is flipped compared to the first one. Before it was aluminum over here, nickel over here. Now we have nickel on the left and aluminum on the right. If we come up from the two-phase region to a super solvus temperature, right? If we're only slightly saturated or a fairly slow cool, right, we get gamma prime precipitation following classical nucleation and growth theory, right? If we come over closer to the phase line and we come down more in the center of the two-phase region, we can get spinodal decomposition, right? We get a phase separation rather than nucleation and growth, right? So this is local ordering and phase separation. And just as a reminder, right, spinodal, right, where we spontaneously come down and we separate into two phases, right? Points B and D are the spinodal points, right? And that's where that's the composition that we will spontaneously separate to. It's not the lowest energy configuration. We can't actually get to the bottom of the well. We need long-range diffusion for that, right? So in spinodal decomposition, we come down to the inflection points on our free energy curve, right? I'm not going to test you on that, but just as a reminder of, right, the sort of the mechanism behind spinodal decomposition, so that if we come down spinodally, we'll have gamma of this composition and gamma prime here of this composition, right? Then we'll need long range. We'll need basically aging time to separate completely to our equilibrium gamma and gamma prime temperature. Yeah, yes, sir.
Can you go back to the slide?
Here?
Yeah.
Yeah.
So I see the primary gamma prime is around the length boundary. which is not desirable in terms of mechanical optics.
Yeah, so gamma, we normally don't want primary gamma prime. So the primary gamma prime is going to form on very long, slow cooling in age, right? So we'll have the gamma prime grains and gamma grains, right? Then solution heat treatment, we typically want to dissolve all the primary gamma prime. But in some situations, we don't actually, right? So we have remnants of the former gamma prime large grains that haven't completely dissolved.
So I was wondering, it has a bad effect, like just because of the great boundary, right? It seems fine. It can act as the particles in the great boundaries.
Yeah, so I mean, so these are sort of grains, right? Think of these on the order of 5 to 10 microns, right? They're not necessarily particles, right? They're actual grains of the ordered compound, right? But generally, we don't want them, right? So we're going to dissolve them away, right? So here's sort of right, our treatment. We come up above the solvus temperature, right? So we have a super solvus heat treatment to dissolve out our primary gamma prime. As we cool down, we develop our secondary, right? Here's our secondary gamma prime, right? And you can see our tertiary gamma prime in between in the gamma channels, right? And notice this is a very high volume fraction of gamma prime, right? So this is a blade alloy, right? Typically, disc alloys will have a lower volume fraction, right? But the effective cooling rate is quite remarkable. So here we see cooling at 200 degrees, right? It's from industry, so it's Fahrenheit per minute, right? Because that's frustrating that all of, like, if you talk to GE or Pratt & Whitney or even Rolls-Royce, right? Everything's in Fahrenheit. It's frustrating. All right, my temperature scale is all sort of wonky. I understand Fahrenheit up to like 500 degrees, like my oven temperature, right? But anything above that, I can't think in F. But you can see here we've got roughly 78% gamma prime fraction, right? And our roughly 170 nanometer size particles for the secondary gamma prime fraction, with the tertiary here, right, about 4%. If we slow the cooling rate, we get more tertiary, a higher fraction of tertiary, a lower fraction of secondary, and the secondary gamma prime are significantly larger, right? And now you can probably begin to see why the creep properties are so good, right? Right? The dislocations are hard to go through gamma prime, relatively easy through gamma, but there isn't a whole lot of them, right? I mean, there isn't a whole lot of gamma. The channels that the dislocations move through in the initial stages of creep are fairly small, right? So in primary creep, we start to fill all these channels with dislocations, and onto secondary creep, we start to cut through all of these particles. Of course, it happens sort of simultaneously, but that's just sort of something to keep in mind, a good schematic. We'll talk more about creep on Wednesday. The other thing we have to keep in mind is our gamma prime phase is not strictly stoichiometric, right? We can substitute titanium out for the aluminum, right? We can potentially have an excess of vacancies on one sublattice versus the other. We can have site mismatches, nickel on aluminum site, right? And then we have other elements, niobium, hafnium, tantalum, are all gamma prime formers, and will partition preferentially into gamma prime. Okay. So microstructures, right? So we got to consider a couple things here. Our composition, right? Oh yeah.
On the last slide, you said that nickel or aluminum atoms might be located on nickel sites.
Yeah.
That's possible, but would that be an anti-phase bound in them to strengthen it, or?
It can be, but you can also have just ordering mismatch. You can also just have a site swap, right? It's just just a different crystal defect, right? But yeah, so if you have a fault, right, from say dislocation, right, then you do have a mismatch, but that's really a planar fault. There, I was just talking really about just a site swap. Okay, so when designing our superalloys, we have to think of a couple different things, right? So our gamma composition, right? Because we also still want to take advantage of solid solution strengthening in the gamma phase, right? We can get significant size bonus out of there. Grain size, of course, is something we've talked about all semester. Precipitation hardening, right? The gamma prime, we'll talk a little bit about gamma double prime, which is a different structure. That some superalloys are strengthened by, but we need to also think about grain boundary chemistry and morphology. So as we go through, we're going to come back to these four key ideas pretty frequently, right? And so grain size with respect to key properties, right? So if we look at this is normalized life divided by strength, right? So it's a nice way to sort of visualizing this. But if we look as we go up in grain size, right, our tensile strength drops from Hall-Petch effect, right? We have significantly better creep properties at large grains. So what does that tell us about the creep mechanisms, right? Grain boundaries at elevated temperatures are going to play a critical role, right? Larger grain, less grain boundary, right? Low cycle fatigue decreases, right? So our two primary design constraints place a conflicting requirements on our microstructure, right? We want good creep, we want good low cycle fatigue, right? So that means we can't necessarily have both. So if we're designing, right, do we think blades, right, that see the hottest part, are we more concerned about creep or fatigue in blades? Creep, right? Blades are single crystal, right? As big as you can possibly make the grain. Let's not put any grain boundaries in, right? What about blades? I mean, what about rotors, discs, right? Discs, right, are taking the whole mechanical weight load of that spinning turbine, right? The centrifugal forces caused by the high spinning basically is the same as hanging a school bus from that blade, from the bottom. You saw that fir tree, right? That's the load on that dovetail, right? Basically, that was the equivalent static load, right? And every time that spins up and shuts off, right, we've got fatigue. So for our discs, we want generally a smaller grain size. Right? There's a big trend to try and do dual discs where you have coarser grains at the edge where you have temperature and finer grains in the hub where you have fatigue cracking. So we have to balance our properties. We also want to eliminate variability in grain size. Right? That should be pretty obvious, right? We want uniform our grain size as possible. Okay, so this is sort of just our table of the key elements broken up by type, right? So these yellow, magnesium, boron, carbon, zirconium, these are grain boundary strengtheners. They'll segregate to the grain boundaries, right? Our gray elements segregate into the gamma matrix, and our purple here, aluminum, titanium, niobium, hafnium, and tantalum, will segregate to the gamma prime. Right? We can sort of further break these down. Right? Classify them a little bit better. The grain boundary strengtheners, the key ones are boron, zirconium, segregate to the boundaries. Right? They reduce the grain boundary energy, give us better creep strength, right? And ductility. Right? Remember, anytime we lower the energy of an interface, we reduce its mobility. Right? We make it more stable. Carbide formers, right? So a list of carbide formers, and these carbides will tend to precipitate at the grain boundaries and reduce the tendency for grain boundary sliding, right, at higher temperatures, right, which are critical for creep. And then we have our solid solution strengtheners, which give us additional strength in both our gamma and gamma prime phase, right? And so here's sort of our sort of the flow chart of all the sort of mechanisms that we're interested in which elements sort of go where, right? If we look at composition, if we look at wrought or powder metal nickel-based superalloys for discs versus that for blades, they have quite a different composition, right? Significantly less cobalt and chrome, higher aluminum, right? So we have a higher fraction of gamma prime formers in airfoils than we do for discs. A key element for current and next generation blades is rhenium, right? Insanely expensive, but gives really important addition to improvement in creep strength, right? So it's sort of like the magic pixie dust that's in the current generation disc alloys. Right. Here we have our just a composition table, right? This is sort of the compositions of all the commercially important existing superalloys. So on to the, right, this is again just for your reference, right? Don't memorize, you don't need to write down compositions, right? But what is sort of important is to know these trends, right? Right. What are the key differences in alloying elements between blade alloys versus disc alloys, right? and why certain additions and subtractions might be made, right? Right, so it would not be out of the question for me to provide an example of a first gen versus a third gen compositions of blade alloys and ask about potential differences in microstructure based on the primary alloying element changes. Right. Okay, so grain boundary carbides. So right, one key thing that we see about the grain boundaries in a lot of the disc alloys is this serrated, tortuous grain boundary path, right? The lower energy we can make the interface, the less straight it has to be, right? The less energy there is associated with curvature of the grain boundary, right? And so which do you think is going to resist sliding better? A nice straight grain boundary or this highly tortuous path, right? Right, and we also have carbides that are going to preferentially segregate to the grain boundary, giving us one. Okay. We do have unwanted phases that show up, right? Some carbides, right? Carbides can be either detrimental or advantageous, right? So that if we are in a disc alloy with grain boundaries, the carbides are going to be beneficial, right? Give us an increase in rupture strength. Carbides and single crystal alloys are, of course, going to be bad because then they're an inclusion. The carbides tend to be cubic and have derivatives of the FCC structure, either the M23C6, so metal 23 carbon 6, or metal 6 carbon type stoichiometry. The other generally unwanted phase are these topologically close packed structures, right? And so these are brittle phases that form during heat treatment or in service, right? So basically, we have close packed atoms in layers, right? And then we have things in between that give us that tend to separate these close packed layers. So we have like a sandwich structure, right? And they're called topologically close packed, right? They're not geometrically close packed, right? That means if you just look at the topology of what's connected to what, right, they have the same connections as a geometrically close packed structure, but their geometry is different, right? They're further separated. These are brittle intermetallics formed as plates, right? The sigma phase, which there's also mu phase and Laves phases, right? The exact structure of these are not important, right? But plate-like or needle-like structure, right? Really bad for mechanical properties, specifically ductility and creep. Sigma is the worst, right? Precipitates out at grain boundaries, right? Sigma is particularly bad because it sucks up all of our strengthening elements to form, so it reduces strength, and then they're very brittle, right? And anytime you have a brittle, nearly interconnected phase at the grain boundary, right, you know that's going to be bad news, right? Because now you got a short circuit brittle path through your entire microstructure. right? So we want to avoid forming these TCP phases at all cost. The difficulty is the things that we're doing to improve our creep strength also increases our susceptibility to forming TCP phases, right? So the same things that are good for creep also tend to want to form these TCP phases. So we have to be very careful about studying phase stability very carefully and the long-term phase stability during service very carefully in superalloy developments, right? So we suck out our refractory phases to form these topologically close packed phases, right? And in blade alloys, they form these needle-shaped structures surrounded by gamma prime. So these are, right, so this gray here is gamma prime. These dark phases are TCP structures. And then, oh good, we're right on time. Get up, observe. So I mentioned gamma double prime phases, right? And so some superalloys, particularly those with high niobium or vanadium concentrations, such as the ubiquitous Inconel 718, right? They don't form gamma prime, and we use a different. They use a different phase for strengthening this gamma double prime, and the structure is based on this nickel 3 niobium or nickel 3 vanadium, right? And it's a DO19 crystal structure, right? It's body-centered tetragonal rather than FCC, right? So it's not as coherent. So we have a coherency hardening effect and an order hardening effect, right? And our lattice parameters we don't have quite the same match.